name's Elisa. This is, like, do you wanna say your name?
Hi, my name's Logan.
I'm Jack.
And this is our project. So our project goal was mostly just to flood the RAM. That's what we decided to do. And we wanted to run a benchmark program that we used to just to measure the performance of the loss due to the flooded RAM. So we just wanted, in this case, we use the matrix multiply. And we expected that the performance on the benchmark program will be severely lowered due to having to swap between the disk and the RAM. And so we used the Raspberry Pi. We both tried the 4 GB RAM and the 8 GB RAM, and we used the operating system of Ubuntu.
Yeah, also we use an SD card that was moderately fast of 104 megabytes per second. And so I don't know if it was clear, but we're using 2 different Raspberry Pis for testing purposes, one 4 GB model and one 8 GB model. And unfortunately, they both have different SD cards, and that will come into play later. But yes, we use Ubuntu Desktop 64-bit. So I think this has probably been covered by other group mates before, but I did want to kind of cover our journey into flooding RAM because it's an interesting one. So my first step was to literally just use a while loop and just malloc and just keep mallocing and see what happens. That was my first attempt. And I'm not even writing any values. I'm just mallocing, and I just wanted to see what happens. And so I ran it on the Raspberry Pi, and you can see the memory go up. And what you don't see is that this is the last screenshot I'm able to take before it crashes. Where it is, yeah. So if you do this with a while loop, it'll just keep mallocing until it literally can't run anything else other than your malloc, and you have to power cycle the device. And so one other thing I decided to do is I was like, hey, what the heck? Let me run this program on my personal computer just to see what happens. And nothing happens. And I was just so confused for the longest time why nothing is happening. And I found out it's because different OSs do different things. Not even all Linux OSs will do the same thing. So for some reason on the Raspberry Pi, mallocing by itself will actually consume memory. But for my personal computer, I actually need to write to it. So just because you malloc and reserve memory doesn't actually mean it's going to allocate it. And so for my personal computer, I actually had to write data to it. And so here, oh, sorry, I didn't specify, but basically a flood is just a structure that I'm using to indicate as 1 megabyte. So right now it's just 1 megabyte of data. Yeah, and so I'm just writing zeros to it. And that does increase my memory on my personal computer. So the point of this slide is to just illustrate that different OSs will do different things. And so it's very important that if you're going to do testing on this, to stick with the same OS, or stick with the same OS, same system. You never know what you're going to get. Okay, so attempt 2. I cannot keep crashing my Raspberry Pi 4. This is not a good idea. I can't do that. So I need to know when to stop allocating RAM. And so my first step was to just, what if I just stop when the virtual memory is full? Well, that's a terrible idea because what happens is you just get a seg fault. The thing is, you'll never reach, like if you do it this way, you'll just never reach, you'll never fill virtual memory without the OS screaming at you. Not that, I mean, that's based off of my findings. I have not found a way. And so that doesn't work. So what I did, it's not an elegant solution, but I just kind of experimentally determined what was the max allowable amount of memory that I could malloc and write to with that and get away with it. And so right here, you can see this is before me running my program. There's please pay attention to the number of memory and also the swap. So basically what I do is I found out that somewhere between 6 gigabytes to 7 gigabytes, which makes sense on my 8 gigabyte Raspberry Pi 4, is the golden amount. If I do 7 gigabyte, it crashes, dead. If I do 6 gigabytes, it allows, and we found out that 7,000 megabytes works really well. And so we decided to use that for all future calculations. So you can just kind of see when we run the program, it'll completely fill up the memory and it'll also increase the swap. So this is what we want. We want to flood the RAM and it works very well. So that's good. Okay, so I could skip the slide. No? Okay. So what we were going to do is we're going to use our benchmark program, which, as Alyssa said, was a matrix multiply. And there's basically this is what we're going to do. There is one initial process that runs at the beginning of our test, and it just creates a matrix on the disk. And it's just, you know, a bunch of numbers. And it's what we want to do is we want to force the OS to read from the disk because we want to get the disk involved just to see what happens. And so that's the initial process. It just instantiates the matrix and puts it on the disk. And then what we have is a looped process. So in a while loop here, that basically just what it'll do is it'll load the matrix from the disk. It'll perform a matrix multiply, and then we'll allocate 1 megabyte of memory. So that's what's going to do. It's going to loop until it reaches k is greater than or equal to 7,000, which is greater than 7,000 megabytes. So once we've allocated 7,000 megabytes, we quit the program because we've determined experimentally that our RAM is flooded at that point.
So to measure kind of our performance losses from filling up the RAM, we basically sandwiched our workload matrix multiply between 2 calls to the clock function from the C timing library. And then every run of that, we got the time elapsed between the start and the end, and then grabbed the amount of memory that we've allocated. We shoved that into a CSV file. And then after our run had completed of filling up the memory, we opened that up with a Python script and then plotted it. And then while we were doing this, we were also looking at the effects on the memory and our disk reads and other statistics using top and what is it, nmon, and then other commands.
Okay, so we wanted to run basically just a baseline test on just matrix multiply by itself without any memory allocation funny business, just to get a baseline. So I commented out the memory allocation and the writing, and it'll just, but I kept the k is greater than or equal to 7,000 to keep the number of iterations the same. So it's just looping 7,000 times. So basically what we notice here is that on the right axis, or on the x-axis, there is memory allocated. Don't think of it as memory allocated, just think of it as loops for now for this one. And on the y-axis, there's matrix multiply runtime, which is in units of cycles of the clock. And you can see that there's this huge spike at the very first time that it runs the program, the very first loop. And then after that, it's, it's spiky, but it's rather consistently flat. And that makes sense because the first time it loads the program, it has to read the matrix from the disk and it's loading it onto the RAM. And especially that's possible when there is space on the RAM. So that makes a lot of sense. So what happens when we actually do memory allocation? So for all of these tests for now, we're using a matrix size of 64 by 64. We'll eventually experiment with different matrices. But you can see that we still have that spike in the beginning. And then afterwards, it's pretty flat. It's because that matrix is in the RAM. But then as we get to the edge, where it's about getting closer to that 7,000 megabyte point, you can start to see that the matrix runtime just skyrockets. And this is very repeatable. You run this multiple times and you'll get the same results. Maybe not as clean, but you'll still get the same results. You want to do it?
Let's see. So we ran into like some kind of strange irregularities in our runs a lot of the times. Occasionally, like if you see here, there's like a random spike kind of in the middle that doesn't really correspond to the memory being like full. That might be due to background processes, other sort of functions of the OS taking up the processing time. We also had like the spike from the beginning disappear sometimes. Not exactly sure as to why. So here it's there, and then the previous one, it is very much gone. We're not exactly sure why that might be.
Okay, so I will make a note that my theory on it was that the reason why the spike isn't there in the beginning is because, oh, it's in RAM from our previous run, and it just happens to be in RAM. And so I was like, what if I just ran the program back to back really quickly so that it doesn't get evicted from RAM? It turns out that it doesn't really work very well. I don't really know what the OS is doing. It's like happen chance if we get that spike in the front or not. I would say it's like 1 out of 10 times we don't get the spike in the front. But yeah.
We also tested using different matrix sizes. We didn't really see too much of a difference in those runs. If we made the matrix too big, however, the RAM just got eaten up super quickly and eventually would seg fault if we set it way too high. So we didn't really glean too much interesting data from that other than the initial sort of spike increasing.
Yeah. So along with what he said, where the first initial spike increases a little bit because of the increased matrix size, what's interesting is that because of the at the end result where it's having to swap between the disk and RAM, it's actually not that much different for the increased matrix size. So that's an interesting result.
So like we said in the beginning, we also tested on a 4 GB Pi. We got some very strange results with what that was doing. Instead of allocating the full range of the memory, I had set it to take off about like 3,800 megabytes of RAM, and it was killed by the OS after about 2,700. And so we didn't really see as dramatic of a slowdown at the end there. Only a couple of spikes that were like 2 to 3 times slower rather than like 4 or more. So we're not exactly sure what the OS was doing in order to kick it out so early and kill the program. But there might be some detection of like the fact that it's allocating so much memory and some early prevention from it crashing the system. And another strange thing that we ran into with this test is that there wasn't any spike at the beginning on any of our runs for this. So despite using the same matrix size in the same code, it didn't have the same performance hit on the first run, which is kind of interesting. We thought that maybe like the differences in the system might be due to like the different SD card speeds, but we're not exactly sure what that might be doing.
So overall, the conclusions, we found that the operating systems, specifically the Raspberry Pi, will not always go to the disk. So we had the problem of, we would see that it was, the swap files would be so low, we weren't sure specifically if it was because of our program or just like the background of just the operating system. And we also saw that the consistency of the free memory went as low as, it was 7,000 megabytes for the 8 gigabyte Raspberry Pi, but then Jack had said for the 4 gigabyte Pi, it like just killed it. So we're really not sure why. There's a reason for that also.
And then overall, if we were trying to do this again and reformatting our experiment, we would probably use a different workload, as the matrix multiply is a lot of spatial locality, which means that the cache can kind of overcome the lack of memory and keep it at a fairly consistent timing up until like the very end of like the memory allocation. And then we might be interested in looking at how the page tables from the virtual memory system fill up the RAM. Like instead of having a single program allocate memory, if we split it up between a ton of different processes, each with their own page table, you might see the RAM filling up without having to allocate it specifically. And then we'd also like to do a different sort of calculation for how the going to disk affects the runtime of a matrix multiply, and hash out like how often it'll be forced to go to the disk and what kind of performance hit that'll take. Thank you.